Hello Zindians, welcome to UmojaHack 2023. My name is Darius Mururi. I'm a data scientist at Zindi. I've prepared for you a starter notebook that I'll take you through. This is the beginner challenge. It's called the Carbon Dioxide Prediction Challenge. It can be found in the Zindi platform. It has a prize pool of $900. With the first person getting $400, the second $300, and then the third $200. The challenge we're trying to solve is to create a machine learning model or deep learning model using open source CO2 emissions data from 75P satellite observations, and then to predict the CO2 levels. The evaluation metric for this challenge is the root mean squared error. I'll take you through the notebook. You can see how you can prepare this submission file down here. And then also it's a good thing also to go through the rules, get accustomed on what's allowed and what's not allowed for this competition. Let's move on to the notebook. So in the notebook, some things that we'll cover include like which libraries you're supposed to use. In this case, I'm using Python, but you are free to use R. And then another libraries that you use, just make sure that they are open source and then they're open to everyone to use. The other thing that we'll be looking at is loading the data, doing some statistical summaries, checking for outliers, doing some exploratory data analysis also, create some features, do some time series visualization, make a simple model, and then also create a submission file that we'll upload to Zindi for scoring. So some of the libraries that we install, one of them is GeoPandas, and then the other is Folium. Usually these libraries are used for geo visualization, like visualizing locations when you are given coordinates of like latitude or longitude. The other libraries that we'll be using include Pandas and NumPy for data manipulation. There's GeoPandas for manipulating coordinates, Matplotlib and Seaborn for visualization, and then we'll be using the sklearn library for modeling. As a data scientist, it's a good thing to set seed for reproducibility so that whenever you run your notebook, you get the same result. So let's load the data and preview. You are provided with three files. We have a training file, a test file, and then a sample submission file. So if you load the training file, this is how it looks like. It has 76 columns, and then we have the ID, latitude, longitude, year, week, and some other features that you can use. These features were extracted from the Sentinel-5P data. The target is the emission. So for each location, which has a latitude and longitude, you are supposed to predict the emission in that location in a particular year in a specific week. We also have the test data set. It's similar to the training set, but the only difference is that it does not have the target value. In this case, the emissions. That's what you are supposed to make your predictions in. So you use all these features to train your model and then make predictions on the test. This is how the sample submission file looks like. The ID, it has the location, the year and the week, and then you're supposed to predict the CO2 levels for that specific location. We can move down and check the shapes of the datasets. We can see that a training file has like 74,000 observations. The test also has like 28,000. So in terms of ratio, we can see that the test is around 30% of the overall dataset. Some statistical summaries from the training file. We can see that we have 74,005 unique locations with different years and weeks. And then in terms of year, we can see that it ranges from the minimum being 2019 to 2022 being the maximum. And then for weeks, we see that it starts from 1 to 52. You can also look in data features and see their summaries. Next thing, we can examine the target, which is the emission. From this graph, we can see that the target is skewed to the right with a value of 17. So these are regression tasks. For regressions, there are some rules that you have to abide by. One of them is that the data you have should follow like a normal distribution. So one thing you can do is that you have to scale or normalize this target to mimic a normal distribution. So there are some techniques we can use. Some of them include log transform, box cogs, or do even a square root transform. So you have to experiment with the different transforms and then build a machine learning model and see whether the performance increases. We can also look at the outliers. We can see that this data has quite a lot of outliers. So you should do the same, like what should you do to outliers? Should you drop them? Should you cap them at some specific number? So it's the same thing as the target distribution. You should experiment with different techniques and then pick the one that suits the occasion. So if we look at the coordinates of the data down here, the data is for South Africa. The green regions are the data that we use to train our models, and then the orange regions is where we are supposed to make predictions on. So use the data on the green regions to make predictions on the orange regions. Also, we can check for missing values and duplicates. In this case, we have both. For missing values, we can see that some features have up to maybe 93% missing values. So you should experiment with different finch engineering or on how to deal with missing values and see which one works best for this case. I've given some tips down here on how you can handle missing values. Next, we can do some EDA. On the years, we can see that the emissions across the years from 2019 to 2022, the data we have is generally representative of each year. There is no imbalanceness, which is a good thing, which is the same thing if you look at the weeks. We see that the weeks have the same amount of data apart from week 49 to week 51. So generally this is a good thing. Some other thing we can check is the correlations of variables. so we can see that the correlations in relation to the target, in this case being the emission, we can see that nitrogen dioxide has the highest correlation with the target. So you might want to do some research on that, on why nitrogen dioxide is more correlated to carbon emissions. And then from that you can get ideas on how to generate new features. We can also represent the same in a correlation plot, which looks like this. You can dive deeper and see which features are correlated and which features that you can manipulate to create new, more informative features from this information. Also, because we have a time feature in this dataset, we can do some time series visualization. If we look, if we take a sample of one region with a latitude of minus 23.73 and a longitude of 28.77, we can see that there is quite a pattern across the years, in that from week 0 to week maybe 20, the emissions are quite low, but then from week 20 to week maybe 35, there's quite a spike, and then after that it resides down. So maybe you will ask yourself, why is this the case? Yeah, if you manage to answer that question, you'll get an idea on how to create the features that will definitely improve the performance of your models. Also, because we have like 4 years and then we have weeks from 1 to 52, which means that there's some cyclic nature in this data, you can create some features from, time-related data, like cyclical features. An example is the rolling mean. Like if you take the rolling mean of sulfur dioxide with a window of 2 weeks, we can see that there is definitely a pattern, which means this feature really can bring new information to the model. So you should think in ways you can create features. This is just one of them. And then you can create the rolling means for other locations, engineer the other features, and then merge the data frames, both for training and test. And then to the good part of modeling. So after doing the feature engineering, filling the missing values with 0 in this case, we can split the data into training and a validation set, so that we can check how our model performs locally. I'll be using the random forest regressor. You can see that I've set a random state, so that if anyone runs this notebook, they'll get the same result that I got. So using this model, I managed to get a root mean squared error of 23,428, which means that for every prediction I make, my error rate is plus minus 23,000, which is, depending on the predictions, depending on the target and the emissions, I think it's worse. So that's why you come in, try to improve this score. Maybe you can get it up to maybe 7,000, even 5,000. Next step is we can analyze the predictions. We can see, like, for this location, for the year 2021, week 24, the emission was this, but we made a prediction of this, and then it means that our error rate is quite high. So it's always good to analyze the predictions just to know how your model is performing, and then see if there's something you can do to improve the model. Like, by analyzing the predictions, they should give you new information on where to improve the model. Yeah. And then if you compare with another location, we can see that we got an error rate which is quite low. So just by looking at this, we can see that our model is struggling when the emissions in a region are quite high. So this one information that we have got from this, we can see that this region, the ground truth is that it has quite high emissions rate, and the model performed poorly. But when the emissions are quite low, our model is able to predict with a very high precision. So I think this might be brought about by the outliers up there. So for you to improve the model, you can maybe drop the outliers or cap them or do something else, and then check whether the model performance improves. If you look at the emissions in the training dataset, the minimum is 0, and then the maximum is around, it's more than 1 million, which is quite high. But then the median is, the mean is 723. So that should tell you something, yeah. It's always a good thing to look whether the features you created are meaningful to the model. We can look at the feature importance plot from the random forest regressor. We can see that the longitude and latitude are quite important. But then on nitrogen dioxide rolling mean, the one that we created, is also has improved the performance of the model, and it's important. So this is just one of the ways you can check whether any feature you create is adding value to your model. The next step is to make predictions on the test set that you have provided by Zindi. You should use the sample submission file to guide you on how to do that. And then finally, you can download that file. You can see here how I create the SSP file. Ensure that you include this index equals to false. This because our backend needs the CSV to be in this format for it to be scored correctly. Yeah, that's it for the starter notebook. This is just to guide you on how to start the competition, but then the real task is up to you on how to create new features, how to do the modeling, how to improve the model, and also how to learn, because in Zindi, there's no losing. If you don't win a competition, you can go away with some quite new information, new skills. So it's a good thing. That's it from me. Have fun and win some prizes.